Okay, we're talking force transformers. Again, force transformers do exactly that. They transform forces. They multiply them usually. So force transformers. Today we're going to talk about the lever. Now, real quick review. What we're really interested in force transformers is mechanical advantage. Again, force transformers are machines that help us make things easier to do. Now, they do not create less work. If force is going to be multiplied, then distances is going to go up. Also, if you're going to multiply the force, you have to increase the distance at which the machine multiplies the force. So we're essentially trading one thing for another thing. Now, under mechanical advantage, there's two different types. There's IMA, which is ideal mechanical advantage. That's if the world was perfect. A perfect world in the machine world means no friction. We obviously never encounter that. That's why it's an ideal situation. We can lessen friction, but we can't get rid of it completely. Now, what we're oftentimes interested in, and what really matters, is the actual mechanical advantage. What does it actually do? Oftentimes you will see that just written as mechanical advantage because it's what it really does. The AMA is nothing more of a ratio of the force you get out of a machine compared to the force you put into the machine. And most of the time that's going to be smaller. Usually we use machines to multiply the force we get out, so the force out of the machine is going to be bigger. Now, let's look at a lever. It's the simplest one. It's the first one we'll do. Now, levers are creatively built into so many different things that we use already, and there are three classes of levers. The first thing, obviously, would be the first class. The first class, lever's a rigid rod. I guess we should say that, actually. It's a rigid bar or rigid rod. And then it has a point at which it rotates about. We call that the fulcrum. If you want to call it pivot point, I'm okay with that. They really mean the same thing. It's a point at which around it's going to rotate. That's essentially a fixed point at which the object's going to rotate around. Now, with a first class lever, this is our familiar seesaw that you may have grown up on the playgrounds. Also pliers, scissors, things like that. And what happens is you're going to place the effort force. That's what you do. Okay, that's you putting stuff into it. You're going to push on that side, and then on the other side, what you're going to do is you're going to pick something up. This is called the resistance force, or oftentimes we call that the load. That's what you're picking up. And the mechanical advantage is simply a ratio of what you pick up divided by what you put in. So if you pick up 500 pounds and put in 100 pounds, the ratio would be 5, so your actual mechanical advantage would be 5. It would be trading it. The lab will explain a lot more about this. Now the next is a second class lever. First class is probably the most common one. A second class lever. Now with a second class lever, what happens now is your fulcrum is way out at one end, and the load that you're lifting is in the middle. So the load that you're going to pick up is in the middle, and of course it's going to want to act down. The weight is going to push it down. So to counteract that, you have to apply an effort force that's going up. So you have to apply an upward force. If you think about, there's one place that these are commonly used: wheelbarrows. There may be other places they're used, but that's by far the most common one. The fulcrum would be the center of the rolling wheel. This would be your mulch or your hay or whatever you have in your thing, and then this is what you do. Remember, effort force is always the effort you put in. Now let's take a look at the last one. Well, if we have a first class lever and a second class lever, chances are the next one is going to be a third class lever. And see how that goes? That's kind of a pattern. You like that? Third class levers are more common than you think. Again, the fulcrum is way out at one end again. That's your pivot point. But now what happens is your effort force is in the middle. And if your effort force, if you push up on that rigid rod, that means your load is going to be pushed in that direction. The load is going to go up. It's always acting against it. So this is your load or your effort force. And if you think about this, this is actually a more common type of lever than you at first glance realize, because quite often we cause things to pivot at one end and we apply a force in the middle. Common things, this: baseball and softball bats. This would be your bottom hand on the bat. This would be the effort force hand on the bat. The load would be hitting the baseball. Brooms. This is the top hand where you're holding it. This is the middle of the broom where you're pushing it. Rakes. Stuff like that. Now, AMA is going to be a ratio of force out divided by force in. IMA, which you'll see in the lab, is going to be a ratio of the distance. It's going to be a ratio of the difference in distances. It's going to be a ratio of the difference. In this case, it's going to be a ratio of the distances. And I'm not going to tell you which is which. I want you to get that out of the lab. But it's a ratio of the distances. And the distance here is going to be the distance from the fulcrum. Okay, the lab will help tie this up a little bit more and make a little more sense with it. And we'll do probably 2 labs on levers. Okay, thank you.